In this video, we will discuss the molecules having more than one J value. So this is the spectra we have discussed in our previous lecture. That's chloroethane. Both protons having different environment like this CH2 and CH3. So they were splitting to each other. CH2 is appearing here at higher chemical set value, CH3 at lower chemical set value. So CH3 is splitting CH2 to quadrat according to N+1 rule, and CH2 is splitting to CH3 into triplet according to N+1 rule. So here CH2 has only one type of chemically non-equivalent proton, while also CH3 has one type of non-equivalent proton. So means there is only one J value. But what if a proton has two types of non-equivalent protons? Then there will be more than one J value, and we will discuss this now. So this is the example of molecule having three different type of protons, means we will get three signal in NMR spectra. If we discuss about this CH2 protons, which is highlighted, this has two types nearby proton, one this CH2 group, other one this CH proton. So both CH2 and CH will split the signal of this CH2 protons. But how they will split? Because the environment of this CH proton is different from this CH2 proton. So the extent of the coupling will be different for both type of protons because both have different chemical environment. So how we will split the CH2 signal in this molecule? Because N+1 rule is not working here. So let's see the spectra. If you see, the CH2 is giving triplet due to this CH2 according to N+1 only, because there is no other nearby protons of this CH2 group. Same, this CH is giving triplet due to this CH2 protons because they are splitting this CH signal into triplet according to N+1 rule. But we don't know what this CH2 will give, because this CH2 also couple with this CH2 and this CH. So this should give more than triplet or doublet. So let's start. For example, if this CH2 couple first with this CH protons, means this CH will split the signal of CH2 into doublet. So we just splitting into doublet. Then this CH2 protons will split that signal into triplet. Means first CH is splitting the signal of CH2 into doublet, and then another CH2 group will split this signal into triplet. So finally there will be two J value. This will be the J1 value due to CH splitting, and this will be the J2 value due to CH2 splitting. It doesn't matter, we first consider this CH2 or the CH proton. We can also take CH2 splitting first and followed by CH coupling. So in this case we are getting doublet of triplet. So we will see this, we will say this signal DT means doublet of triplet, and here we will have two J value, J1 and J2. So in this example, J1 is due to CH proton and J2 is due to another CH2 group. So this is the peak for this highlighted CH2, which is a doublet triplet, but it's not separated well because there is no very good separation between doublet or triplet. So it looks like a multiplet. So sometimes due to low separation between the peaks, we see overlapping of peaks and we simply say it multiplet, because in this we will not be able to calculate clearly the J1 and J2 value in some time. Let's see the other example. This CH2 protons has two types of neighboring proton, this methylene proton and this aldehydic proton. So let's see first this aldehydic proton coupling with this CH2 giving the doublet as a J1 coupling, and now this CH2 will couple this signal again into doublet according to N+1 rule. So finally we will get doublet of doublet. So doublet of doublet, because this CH is giving doublet and then another CH2 coupling that doublet into doublet. So finally we are getting doublet of doublet. Now how to calculate this J1 and J2? So for calculating J1 value, we have to take the distance between peak 1 and 3 or peak 2 and 4, and then that will give this distance multiplying by the operating frequency will give the value of J1. If we take the distance between 1 and 4 to calculate J1, that will be the wrong. Every time we have to take the distance between 1 and 3 or 2 and 4 to find the J1 value. To get the J2 value, we have to take the spacing between 1 and 2 or 3 and 4 and multiply it by the operating frequency. That will give us the value of J2 coupling constant. Other example, we have CH proton, CH2 proton, the nearby proton of this CH2 group. So first CH proton will couple this CH2 into doublet, and the another CH2 group will split this doublet into two triplets. So finally we will get doublet of triplets. Now how to calculate the J value? First we have to calculate the J by measuring the difference between the most intense lines, that's the 2 and 5 lines in hertz, and multiply it by the operating frequency. So the distance between these two peaks will give J1, and the distance between any these two peaks like 1 and 2 or 2 or 3, 4 and 5 or 5 and 6 will give the value of J2 coupling constant. This is an example of substituted benzene. So if we see the coupling pattern for this proton has this proton as at 3 bond distance. So this will be give the highest coupling in magnitude, and these two proton will give the meta coupling because they are 4 bond distance. So as we have seen in the aromatic compound, there is a long range coupling also observed. So first this proton will couple to this blue proton in the doublet. Now this doublet, for example, due to this proton splitting into another doublet, so that, and then the third proton will split this doublet into another doublet. So finally we will get doublet of doublet of doublet, means 3DDD. So now we will get for this blue proton this type of pattern, means doublet of doublet and doublet. So how to calculate the 3J value in this example? So for calculating the J1, we have to take the distance between 1 and 5 peaks. To calculate the J2 value, we have to take distance between 5 and peak 7. To calculate J3, we have to take the distance between 3 and 4 or 5 and 6 or 7 or 8 or 1 or 2 peaks. That will give the coupling constant value for J3. So this is the way to find more than one J value in molecules having more than one type of protons. Now what happens if n+1 rule fails? Because previously we have applied n+1 rule in molecules, but if it got failed, like just take the example, these two examples. Here there is a free rotation between CC bonds, so HA and HB will be equivalent protons, means they will couple with SC with the same magnitude, means the coupling chemical shift value of A and B will be same because they are chemically equivalent proton, and they will couple with SC proton, means JAC will be equal to JBC, and there will be no splitting between A and B proton because they are chemically equivalent protons. So they are coupling with SC according to n+1 rule. But if we see, we stop this rotation between CC bond. Now HA and HB become chemically non-equivalent protons. Now the chemical shift value for HA and HB will be different, and they will couple with SC with a different extent of coupling constant, means the JAC will not be equal to JBC, and they will also couple with each other, means JAB will not be 0. So now here n+1 rule getting failed. So how to calculate the coupling constant in this case? So we have seen the example of diisotropic protons where n+1 rule will not work, or vinylic proton on vinylic carbon, they also are chemically non-equivalent protons. So let's see the example of these two molecules. In this molecule, the blue proton are chemically equivalent and the red proton are chemically equivalent. So they will couple to each other by n+1 rule. So we can calculate easily their splitting pattern using n+1 rule. But if we replace one proton, means red proton, by chloro group, now this molecule has a chiral center at this carbon. So now these two protons become diisotropic proton, means they will couple with each other also and will appear at different chemical shift values. So as you can see in this spectra, these blue protons are giving signal at two different chemical shift value, means they are chemically non-equivalent protons. So they will couple with each other also. So here n+1 rule will not work because we see first this for this proton, this will couple with both of them. So this two blue proton will split this red proton with a different extent because they are chemically non-equivalent proton. So here n+1 rule will not work. We have to apply the tree diagram as we have applied in previous slides. So means this H will split this red proton to doublet, and again this blue proton will split that doublet into doublet. So finally we will get doublet of doublet for this red proton, and same for this blue proton. We will also get doublet of doublet for each blue proton here. So this is the molecule where n+1 rule is not working. We have to apply tree diagram. Now we will see what are magnetically equivalent proton. As we have seen previously, chemically equivalent proton. Chemically equivalent proton, those appearing at the same chemical shift value, or they are chemically same and they do not couple with each other and giving only one signal in NMR. But what are magnetically equivalent proton? To be magnetically equivalent, proton should fulfill these two conditions. First, they must have identical chemical shift value as in case of chemical equivalent protons, and second, they must couple with all other nuclei in the molecule to same extent or to same J value. So we have to look for the second condition. Let's take the example of this substituted benzene. In this, the HA and HB are chemically equivalent proton, while SC and HD are chemically equivalent proton. So HA and HB will give one signal, means they will appear at same chemical shift, while SC and HD will also give one single peak, they will appear at same chemical shift value. But if we see in this, HA couple with SC due to 3 bond distance, but HB does not couple with SC because it has 5 bond distance from SC. So you can see between these two chemically equivalent proton, HA is coupling with SC, but HB is not coupling with SC. So HA and HB are chemically equivalent, but they are not magnetically equivalent, means they are magnetically non-equivalent proton. And same will be for SC and HD, because if we see couple with HA because it is to 3 bond distance, but HD will not couple with HA because it's a 5 bond distance. So SC and HD also magnetically non-equivalent proton. So all magnetically equivalent protons are chemically equivalent, but all chemically equivalent protons are not magnetically equivalent protons. Thank you very much.